My name is Sivram Ramanathan. I'm a fifth-year PhD student at the University of Southern California, and today I'll be presenting our work on quantifying the impact of blocklisting in the age of address reuse. This work is in joint collaboration with Tanisha Hussain, Elena Merkovic, Milan Yu, and Sadia Afroz. What are IP blocklists? IP blocklist contains a list of IP addresses that are known to be bad, and they are commonly used by network operators to defend their network. Some of the commonly used publicly available block lists are listed here, and they include Alien Vault, Spamhaus, or Project Honeypot. However, using IP address as an identifier for malicious entities can be problematic. This is because IP address can be reused, and blocking reused addresses can block more number of users than intended. Now let's look into this problem on two cases of address reuse. The first case of address reuse is using network address translation. And let's consider this example of a user who's trying to access a website hosted on Cloudflare. This is a real-world example which we found in the Cloudflare community blog. Um, this particular user attempts to access this particular website using an IP address IP, and when they tried to access the website, they were blocked. And the user found out that their IP address was listed in the DShield block list, which is used by Cloudflare to actually prevent connections from unwanted users. Now, the user goes ahead and contacts their ISP and finds out that their IP address is in fact being shared by multiple users at the same time using NAT. On probing further, they found that another user using the same IP address was running a spam campaign, thereby all the users sharing the same IP address were actually blocklisted because of this one malicious user. So, users can be unjustly blocked if their IP address is shared because of NAT. Let's consider another case of address reuse due to dynamic addressing. Now let's consider an example where there are two users A and B who are allocated IP addresses IPA and IPB. Now let's assume that user A is malicious and is kind of running a malicious campaign, thereby they are blocklisted in a particular blocklist. Now over time, due to dynamic addressing policies, user B could actually be allocated IPA because of some particular policy. Now what can happen is that user B can also can be blocked because they're being allocated a previously blocklisted IP addresses. Therefore, users cannot be unjustly blocked when they have been allocated an IP address that have been previously blocklisted. So what we can see is that IP address can be reused at the same time or can be reused over time, and this can be problematic when they're being blocklisted. So the rest of my talk is divided as follows, where first we look into the usage and the perception of blocklists among network operators. Then we propose two techniques to identify reused addresses. Then we compare the reused address with the blocklist data set and see how prevalent reused addresses are on blocklists. Then we go ahead with evaluation, and finally I'll conclude the talk with summary. So, in order to understand the usage of blocklists, we communicated to network operators by sending out a survey through network operators mailing list, and we got response from 40 network operators. The key idea of the study is to actually understand the usage of blocklists and also understand their anecdotal experience of inaccuracies in blocklists due to address reuse. There are two key observations which we got from the survey. The first observation is that blocklists are commonly used, and they're also used to constantly block attack traffic. We find that about 70% of network operators use blocklists, and about 60% of them to actually use them to block attack traffic. The second key observation is that blocklists can actually have inaccuracies due to address reuse. We find that about 56 to 76% of the network operators feel that the inaccuracies in blocklists could be due to address reuse because of natting or dynamic addressing. More details of the survey could be found in the paper. Now, the key idea of our study is as follows. First, we want to accurately identify reused addresses. Then, we want to check the presence of reused address in block lists. And finally, we want to quantify the impact of blocking these reused IP addresses in block lists. At first, we proposed two techniques using the BitTorrent DHT crawler and also the RIPE Atlas measurement logs to identify reused addresses, including NAT and dynamic addresses. Then, we compared the reused addresses with 151 publicly available block lists, which actually monitored different types of attacks. Finally, we estimate the impact of blocking IP addresses that are being shared using our techniques. So, let's go ahead and see our technique of detecting NAT addresses. We use a BitTorrent network to actually identify users that have been allocated the same IP address. The BitTorrent protocol allows different messages, but our crawler makes use of two messages to identify multiple users using the same IP address. The first message is the getNodes message, which actually returns a list of active neighbors for a particular BitTorrent user. Then the second message is a BitTorrent ping message, which the user actually uses to check the active neighbors in among the neighbor list. Now, the BitTorrent protocol mandates that whenever the user receives these two messages, they are supposed to reply back to these two messages. Now, using this, we built our crawler. So let's take this example where the crawler actually uses the getNote message to identify a bunch of users in the BitTorrent network. Now, in this example, it identifies 5 users with 3 IP addresses. Note that IP1 and IP2, which are highlighted in yellow, are being allocated to 4 potential users with different port numbers. Now, in order to verify that these are indeed active users behind the same IP address, the crawler sends the BitTorrent ping messages to each one of the IP addresses and 2 BitTorrent ping messages to them. Now, the crawler waits for the responses, and in this example, it receives 2 replies from IP address 2, but it receives only 1 reply from IP address 1. Now, this is expected because when the crawler is traversing through the BitTorrent network, what can happen is that it could encounter through stale information where a particular user may have shut down their computer and the particular stale information is still in the DHT table, which will be encountered by the crawler. So in order to prevent the stale information, what we do is that the BitTorrent verifies using the BitTorrent ping messages to see whether they are actually active behind the same IP address or not. So again, in this example, we find that IP address 2, since they replied to from 2 different port numbers, we know that there are at least 2 active users behind the same IP address. So therefore, we say that IP address 2 is using a NAT. Using this particular technique, what we can verify is that getNodes can identify the set of IP addresses that are being shared, and BDPing can ensure that they are active users. Now, using this technique, we identify about 48 million IP addresses that are using BitTorrent. We sent about 1.6 billion BitTorrent big messages, and out of which we actually got response from 48.6% of them. And using a technique, we identified 2 million IP addresses that are using NAT. Now, let's go ahead to a technique for detecting dynamic addresses. For this, we use RIPE Atlas probe measurement logs to determine probes that are present in dynamically allocated regions. So RIPE Atlas probes can be installed by volunteers in their own network, and each RIPE Atlas probe is allocated a unique ID. Periodically, the RIPE probe actually communicates with the central infrastructure, basically telling what their allocated IP address at that particular moment be. So for instance, the logs could be as follows, where this particular RIPE Atlas probe with an ID has been allocated an IP of IP4 over time T1 to T3. Now we use this measurement log to pretty much determine whether the RIPE Atlas probe is located in a dynamically allocated prefix or not. Now, let's take an example where, at say at time T4, this particular ID, RIPE Atlas probe, is actually allocated an IP of IP6. Now, we can potentially note that this particular probe is in a dynamically allocated region. However, it's not all that simple because among the 15,000 RIPE Atlas probes, the probes do go through address changes, but it need not be dynamically. It need not mean that they are in a dynamically allocated prefix. So in order to prove this, we have a 3-stage filtering process. At first, we remove probes that change IP address across different autonomous systems. This is done to prevent users who have actually shifted their ISPs. So they're not exactly in a dynamically allocated prefix, but more often they are given a new IP address from a different autonomous system. So therefore, they're not dynamically allocated. So once we apply this filter, we have filtered down to about 13,600 RIPE Atlas probes. Then, what we do is that we only consider probes that periodically change their IP address. So consider this particular graph where the x-axis indicates the total number of RIPE Atlas probes and the y-axis indicates the total number of IP addresses that have been allocated to the probes in our monitoring period. Now we estimate the knee of the graph to determine probes that frequently change the address, and the knee is estimated to be about 8 addresses in this particular scenario. So we only consider the probes that have at least changed, that have been allocated at least 8 different IP addresses. Once we apply the filter, we are only left at about 2,600 RIPE Atlas probes. Finally, we only look into probes that have been that change their addresses very frequently, that is in the order of days. So this is important because we want to only consider probes probes that are present in address prefixes that cause maximum impact if they're being blocklisted. So once we choose these particular probes, we are only left with 629 RIPE Atlas probes. Now, let's look into the Blocklist data set, which we use to compare or identify reused addresses that are being listed in them. So we use a black data set that actively maintains publicly available block lists. They consist of about 151 different block lists, which consists of block lists for different attack types, including spam, DDoS, or reputation of IP addresses. Our study was conducted over 83 days over 2 different measurement periods. The first measurement period started in August 2019 and went up to September 2019, and the second measurement period started in March 2020 and went up to May 2020. In this period, we observed about 2.2 million IP addresses that were blocklisted. So, what we do is that now we check the overlap between the blocklist dataset and the reused addresses identified by our technique. For the natted addresses, we have already seen that we saw about 48 million IP addresses that use BitTorrent, and out of them, only 2 million IP addresses have 2 or more active users behind them, therefore they are natted. Now, when we overlap this 2 million IP addresses with our blocklist dataset, we get about 29,000 IP addresses that are natted and are also blocklisted. In case of dynamic addressing, we see that about 53,000 IP addresses are blocklisted and are also present in the same region as that of RIPE Atlas probes. Now, when we apply the first filter of removing the probes that are present that allocate address across different autonomous systems, we are left with only 34,000 IP addresses. Then, when we only consider RIPE Atlas probes that change their addresses frequently, that is probes that have been allocated at least 8 different IP addresses, we are left with about 33,000 IP addresses that are also blocklisted. Then, when we consider RIPE Atlas probes that change their addresses very frequently, we are left with 22,700 IP addresses that are both blocklisted and are potentially in a dynamically allocated region. Now, let's move on to our evaluation and let's try to answer some interesting questions. First, how many block lists actually list reused addresses? The left figure actually shows that for the natted reused addresses, and the right figure shows for the dynamically allocated reused addresses. Now, in both the graphs, the x-axis indicates the total number of blacklists, and the y-axis indicates the addresses that are being reused in these blacklists in our monitoring period. What we observe is that about 61 blocklists do not have any natted addresses 61 blacklists do not list any natted reused addresses, and about 72 blocklists do not list any dynamically allocated reused addresses. We observe that top 10 blocklists actually contribute to the most number of reused addresses. In case of natted addresses, about 65% of them actually list all the natted reused addresses, and in case of dynamic addresses, about 72% of them list all the dynamically allocated reused addresses. Finally, we compare a technique with probably the only reproducible technique, and we find that the number of dynamically allocated reused addresses detected by their technique is equivalent to ours. The second question we ask is that how long are these reused addresses listed in block lists? This is particularly important because if reused addresses are listed for a longer time, that means that they could affect these users for a much longer time. What we observe is that reused addresses are removed much faster than the other addresses. The graph shows the number of days the number of days the IP addresses are present in block lists, and the y-axis is a CDF of all the addresses. What we find is that among the reused addresses, dynamically allocated addresses are removed much quicker. We see that within 2 days, 77% of all the dynamically allocated reused addresses are removed within 2 days, when only about 42% of all the other blocklisted addresses are removed within 2 days. The final question which we're trying to answer is that how many users are actually affected if the IP addresses that are present in blocklists are being used to actively block the traffic. Now, the graph here shows the number of users affected on the x-axis, and the y-axis indicates the CDF of all the IP addresses. Now, given that the BitTorrent crawler can actively detect the total number of active users behind the same IP address, we could actually estimate the lower bound of the number of users that could potentially be affected if they're being blocked. So if we find that some IP addresses, if they're being blocked, if they're being used to block, they can actually block about 78 users at the same time. Now, many of the IP addresses only have 2 active users behind them, about 68% of them. And finally, we find that about 98% of the IP addresses have less than 10 active users behind the same IP address. Now, in summary, I'll try to talk about how this particular list could actually help others, and I'll move on to the conclusions after that. So we make our dataset public, and all our scripts for the crawler and the IPATLS probes are public as well. And we feel that our blocklist could actually, our technique could actually help in 3 different ways. First, to the network operators. The network operators can use our list to actually build a better defense mechanism, such as gray listing, where our list could be part of a gray list, where the traffic from these sources could be diverted to a more sophisticated system rather than outrightly blocking these addresses. We also feel that our list could help blocklist maintainers to maintain better and accurate block lists, where they can actually provide a separate list using our list to actually say that these could contain a mix of both malicious as well as legitimate users. Finally, we feel that our list could actually help other services like Cloudflare or Google that could actually put warnings to users indicating that telling the users that they're sharing their IP address with other malicious users, and thereby they can ask their ISPs to actually help them clean the other users who are conducting malicious campaigns. So finally, our techniques do have limitations. So in terms of detecting NAT, our technique is limited only to BitTorrent users, and they're also limited to IP addresses that have only at least two active users behind the same IP address. Now, many users are known to turn off their computers when they're not using BitTorrent, and therefore we would miss addresses that are actually NATed, but just because they're not, the machines aren't on, we wouldn't be able to capture them. Moreover, some ISPs could actually outrightly block all the BitTorrent traffic, so our visibility in these networks is limited. So in terms of detecting dynamic addresses, our technique is limited to IP prefixes that have IPATLS probes in them. And this is extremely biased towards certain geographical regions such as North America and Europe. And we may also miss IP addresses that have been allocated to different autonomous systems belonging to the same ISP. And of course, we do have limitations of exact IP boundary prefix, the prefix boundary detection for dynamic addresses, and therefore we may miss out some IP addresses that are actually dynamically allocated. So in conclusion, we propose 2 techniques to identify reused addresses in blocklists. We detect reused addresses in using about 151 publicly available blocklists, and we find that about 60% of these blocklists at least list 1 reused addresses. Our NAT detection technique has also found that some blocklists have IP addresses in them that could actually affect more than 78 users. Our datasets are public, and it could be found in the links given here. So thank you for your time. And again, the links to these particular data set and also to the Blacklist data set is present here. Thank you.